Today we're going to continue looking at those periodic trends, and today we're looking at specifically the ionization energies. So ionization energy is the energy required to remove a loosely bound electron from an atom to form an ion, a cation. So real simply, it's just the energy required to remove an electron from an atom to form a cation. And we can talk in terms of like first ionization energies, second ionization energies, third ionization energies, etc. But when we talk about ionization energies, we're really only looking at the first ionization energy. Okay? So we're going to look at the trends in terms of first ionization energy only. So the general trend is that the second ionization energy is always larger than the first, and the third is always larger than second, just because it takes more energy to remove an electron from an ion than it is from a neutral atom. So when we talk in terms of energy and movement of matter, you need to think back to your 8th grade physical science year and remember that energy is either kinetic or potential. And in order for work to happen, which is force times the distance, you have to have energy. So we're talking about moving matter, moving electrons. Therefore, think in terms of the octet rule. Is it less energy to move 1 or to move 7? So if, for example, a group 1 element has just the 1 valence electron, is it easier to move 1 and have an octet? Or is it easier to move 7 and have an octet? Energy-wise, it's easier to remove 1. So, and not only that, but these electrons can also be held tighter the further in you go. Okay? So the general trend, again, there are exceptions. We only care about the general trend. What do most of them do? Well, most of them increase in their ionization energies as you go across a period, which makes sense because if you'll remember, that nuclear charge increases. That means they're held on tighter to the nucleus of the atom, and they're attracted more. And those valence electrons are attracted. But as you go down a group, they're held looser. And that's, again, the properties of metals. And they have 1 or 2 valence electrons, and they're held loose because they have a greater shielding effect, affects them. Okay, and there's greater repulsion with their other electrons. There are exceptions. You don't have to know what those exceptions are. You'll actually see them on this periodic table here in a minute. But just note that because of the way these half-filled and filled subshells are, the S and the P's, then the energies do change for some of these elements. And you'll find something kind of unique happens with beryllium. It has the ability to form both covalent and ionic compounds. So we're going to look at this example again. Let's see if I can make this work. I don't know why I can't make my little arrow thing go away. Okay, let me turn that off. There we go. Oh, I'm learning how to use this. Okay, so let's look at, again, ionization energies. And again, it gives us a scatter plot, which is always the best way to look at it. So we have lithium. As you go across a period, we see that they increase, and we end in neon because it has an octet, so it doesn't really like to have any electrons removed. So they're loosely held with those metals. Notice we got a few anomalies here. See how those between the boron and carbon changes, and then here between nitrogen and oxygen changes. You just, in general, they increase. And then as you go down the group, what happens? They decrease because it's easier to remove loosely held electrons. Okay, so another way to look at them is with the ball. Again, you'll see a few exceptions. So as you go across a period, notice the ionization energies increase, and as you go down the group, you notice that they decrease. Okay, it's harder to see with these metals over here, but here they are with the non-metals, easier to see. And then when you hold your mouse over one of them, you can see all the different ionization energies. Notice how the ionization energies increase with each successive ionization. Okay, so this is why non-metals tend to form negative ions, and it's easier to gain electrons than to lose to have an octet, and this is why metals tend to lose electrons and form cations to have their octet. Okay? So, look at your little tab, and you'll want to pause the video while you try to figure this example. So, let's look at strontium, beryllium, calcium, and magnesium. So when we look at the periodic table, we see that strontium, beryllium, calcium, and magnesium are in the same group. Look at your little labeling of your periodic table and put them in order from smallest to greatest, and then don't forget to hit pause while you do it. So you should have said strontium has the smallest ionization energy and beryllium has the largest. Since they're in the same group, remember the ionization energy decreases down a group. Let's look at these. We've got aluminum, chlorine, sodium, and potassium. So if we look, we see that aluminum, chlorine, sodium, and potassium are in the same period. So you want to hit pause, use your little periodic trends table, and figure out the order. So we see that sodium has a smaller ionization energy. It's easier to lose a loose held valence electron, whereas chlorine has a large ionization energy, and it doesn't like to lose electrons. It likes to gain them and form an anion.